UK. Welcome to the 9th Surface Ventures webinar. Before we go any further, can you just write where you're joining us from today in the chat box on your right-hand side, just so we can see everything works. Great, that seems to be working. Seems that works fine. Many great places there. So to begin, my name's Tahid Khan. I'm a VP and Vice President at Surface Ventures, and I'm your host for today. To give a bit of background about Surface Ventures, we're a non-for-profit organisation, and our mission is to provide world-class surface engineering education for academia and industry. So every month, we aim to bring you a sector-leading speaker to present the current challenges and future trends in surface engineering. So today it's my pleasure to introduce Professor Cheng, who will be talking about measuring the coupled electrochemical-mechanical behaviour of materials for making better batteries. Professor Cheng is the Frank Derbyshire Professor of Materials Science and Professor of Physics and Astronomy at the University of Kentucky, where he has worked since 2008. Previously, he was a technical fellow and lab group manager for engineered surfaces and functional materials at the General Motors Research and Development Center. He graduated from the California Institute of Technology with a BS degree in physics and mathematics and an MS and PhD degrees in applied physics. So in terms of an agenda, we will start with the presentation, then switch for a few minutes to our sponsor, Micromaterials, and then we'll come back to the presenter for your questions. We are planning for the session to be around 60 minutes in total. However, depending on questions, this may go slightly over, so we do appreciate your understanding. There will be a quick GDPR announcement. There'll be a few brochures and application papers for Micromaterials. And if you do download them, someone from the company will get in touch to provide further support. And just a reminder about our website, which is surfaceventures.org. It features videos from our previous talks, information regarding upcoming webinars, and information about our Surface Ventures team. So please do take a minute to go and visit. So we're going to do a quick poll, like we always like to do, and we have a quick question. And the question today is, are you in academia, industry, or other? So it should be coming on your screens any second now. There we are. Great, we've got a nice mixture. So on that note, I'd like to hand over to our speaker today. So Professor Cheng, over to you.
Well, good morning. Thank you, Tahid, for the nice introduction, and thank you for the opportunity to make a presentation. Today, I will discuss several measurements of materials for developing lithium-ion batteries. As we all know, the 2019 Nobel Prize in Chemistry was awarded to 3 pioneers in the lithium-ion battery technology. Professor Stan Whittingham, then working in Exxon Research Center in the 1970s, developed a rechargeable lithium-ion battery using the titanium disulfide as the positive electrode and metallic lithium as the negative electrode. This battery can produce about 2 volts. However, the metallic lithium metal, has the propensity of forming whiskers or dendrites that can penetrate the separator and cause internal short circuit. And that'll be a safety problem. In the 1980s, Professor John Goodenough proposed the use of metal oxides instead of sulfides as the positive electrode. And with this positive electrode, the reversible the battery can produce 4 volts. And this good enough positive electrode coupled with a graphite negative electrode proposed by Akira Yoshino enabled the first commercialization of lithium-ion batteries. Since then, lithium-ion batteries have revolutionized our lives, as evident from the ubiquitous uses of lithium-ion batteries in our cell phones and in the electric vehicles. Today, there's a worldwide R&D activity to further develop the lithium-ion batteries, to have higher energy, more power, lower cost, and safer. There are many materials that are known to have higher capacity than the graphite negative electrode. Showing here, for example, is silicon. Silicon theoretically can have 10 times higher capacity than that of graphite. However, silicon, like many other high capacity materials, will experience very large volume changes as lithium enters into the silicon and as it comes out of silicon. The volume change can be as large as 300%. Not surprisingly, therefore, the silicon electrode would crack after just a few cycles. As showing here are some of our experiments that with increasing thickness of the silicon film, the cracking pattern changes from nucleation-dominated behavior to crack growth and propagation. And that can be, the change in the cracking pattern can be captured by a very simple computer model showing on the side. And this, furthermore, the experiments and simulation shows that if the film thickness is sufficiently small, less than, let's say, 100 nanometers, cracking can be avoided. But a thin film electrode with less than 100 nanometer in thickness doesn't store much energy. So that is not the practical configuration of a commercial battery. Typically, commercial batteries would consist of active materials in the form of particles, mechanically connected by polymeric binder, and electronically connected by carbon black in a composite electrode configuration. And some time ago, we did a study of diffusion-induced stresses in spherical particles. And our model took into consideration of the effect of surface tension and surface elasticity, and showed that as the size of the particle decreases, the particles are less likely to crack. That is because surface stress can exert an overall compressive stress inside the particle, and particles are less likely to crack under compression. And this effect is stronger as we decrease the particle size down to nanometer length scale. So today we know we can avoid cracking of silicon electrode by either having very thin electrode or by incorporating silicon nanoparticles in a composite electrode. And still, because of the volume expansion and contraction, large stresses can be generated in the silicon composite electrode, as shown here by these images of a bilayer cantilever consisting of a electrode layer on top of a 20 micrometer copper foil. The stress is so significant that the curvature change can be observed visibly with a simple video camera. By analyzing the curvature and by measuring the thickness of the electrode, one can obtain both the elastic modulus and the stress in the electrode. And that is, but more details can be found in these publications. Not surprisingly, therefore, electrodes can crack, as shown in this video. Showing here is that the lithium goes in and out of the electrode. As lithium comes out of the electrode will shrink, causing the cracks to open up. And as lithium enters into the electrode, volume would expand and close the cracks. And this process can be repeated for many, many cycles. On this slide are images of silicon composite electrodes made of different types of polymers as binders. For example, PVDF, naphthalene, and sodium alginate. Quite surprisingly, as you can see, cracking can occur in the electrodes. Quite surprisingly, the one that does not have many cracks, such as in the case of using PVDF as a binder, this binder is a very ineffective binder for silicon electrode in terms of the cycle life of the electrode. This motivated us to study the mechanical behavior of composite electrodes. There are a number of contributing factors that may affect the overall mechanical behavior of the composite electrode. For example, as lithium enters into the silicon, it forms an alloy. One can expect the mechanical property of this alloy changes as a function of composition. And as I mentioned, there is substantial volume change of the particles, which can also cause porosity change in this composite electrode. Furthermore, the polymeric binders can soften under the influence of the organic electrolyte. So which of these factors are more important is something that we wanted to figure out. The mechanical property measurement of electrodes can have several challenges. For example, all these materials are air and moisture sensitive, and we have to avoid the influence. We therefore have to perform mechanical property measurement in an inert environment. There have been some studies, both from density functional theory calculations or mechanical property measurement, showing that silicon lithium alloys, the Young's modulus would decrease with increasing concentration of lithium in silicon. This is not surprising because silicon is covalent bonded, whereas lithium is a very soft, low melting point metal. As we put more lithium into silicon, modulus is expected to decrease. The question then is, what is the mechanical behavior of the composite? And here we use nanoindentation, instrument indentation, to measure the mechanical properties of the composite. Indentation is something that we worked on some years ago when I was active in the surface engineering community. And then here we use it for our battery research. We put a nanoindenter inside the glove box. Furthermore, we developed a sample holder that would allow nanoindentation of samples immersed in under organic electrolyte. We prepared our samples by electrochemically introducing lithium into the composite electrode, and then disassemble the switch lock cell and take this electrode with different concentrations of lithium to the nanoindenter without exposing the sample to air. And because, so we can measure the mechanical property of this composite electrode either under dry or wet conditions. The indentation was quite deep because about 1500 nanometer in depth. This will allow us to cover a large number of silicon particles to obtain results of the composites. And because of the random distribution of pores and surface roughnesses, a large number of indents were made on each sample. About 50 to 100 indents were made on each sample. That allows us to produce a histogram of the hardness values and modulus values. If we plot the average values for modulus and hardness, this is what we learn. First, we learn that the PVDF binder under wet condition is softer than that under dry condition. It's not surprising because PVDF swells under the influence of organic solvent, organic electrolyte. The mechanical property of the composite modulus and hardness also are lower under wet condition than under the dry condition. And that's because of the softening of the binder. More importantly, we saw that the modulus and hardness increases with increasing lithium concentration. And this is opposite from what we know about lithium silicon alloys. For the alloys, the modulus would decrease with increasing lithium concentration. So what's going on? We measure the porosity of the electrode and found that as we lithiate, as lithium enters into the electrode, the porosity decreases. This is because during electrochemical cycling of the battery cell, the electrode is constrained by the cell casing. Therefore, as the silicon expands, the electrode porosity will decrease because the constraint, the total thickness cannot change to accommodate all the volume change of the silicon particles. So the porosity decreases during lithiation and then increases during delithiation. And that can be verified by these cross-section images of the electrode under the indent. The electrode, freshly made electrode under full lithiation and under full delithiation. And as these images show that the porosity indeed change as a function of lithium content. The images also help us understand the deformation mechanisms. When the porosity is high, the deformation is mainly caused by the deformation of the binders. and the densification under the indent. When the porosity is low, when silicon is filled with lithium, the particle size increases, porosity decreases, deformation is caused by both the polymer deformation as well as the deformation of the silicon lithium alloy particles. Although the modulus of each individual particle decreased, but because of volume change, the solid fraction increased upon lithiation, so the overall modulus and hardness increases with lithiation. And that is our understanding of, that is our measurement of the silicon composite electrode. And since then, we have measured composite electrodes made of different polymer binders. And these measurements help us understand why some binders work better than others. So that these are reported in the papers I cited here. My next example is the measurement of mechanical properties of metallic lithium. And lithium was proposed in the original suggestion of invention of rechargeable lithium-ion batteries, but there's a problem with the dendrite or whiskers. Currently, there's a renewed interest in using lithium as the negative electrode because if it can be done, there will be no additional weight from the host species, such as carbon or silicon. So there's active research on how to either prevent dendrite from forming or blocking the dendrites from penetrating through the separator. There are two general approaches. One is to use what's called an artificial solid electrolyte interface. But in the surface engineering community, that will be simply a coating deposited on the surface of lithium metal next to the separator. And the goal is to suppress lithium dendrite growth. The second approach is to use solid electrolyte, solid state electrolyte, which can be polymers or ceramics or polymer ceramic composites. In this community, many people believe the modulus of the solid electrolyte, the shear modulus, should be 2 times of that lithium metal in order to block lithium dendrite penetrating through the solid electrolyte. And this model, of course, is based on the assumption that lithium deforms elastically during the operation, during dendrite growth. So this is a motivation for us to measure the mechanical properties of lithium at room temperature. Again, the measurement of a mechanical property is non-trivial because lithium is reactive, highly reactive. It can react with oxygen and nitrogen and moisture in air. So measurement can be challenging, and there are only a few reported values in the literature. And the data, the Young's modulus value reported previously do not agree. And furthermore, room temperature is a relatively high temperature for lithium, since lithium melts at 170 Celsius. So the ratio of room temperature to the melting temperature of lithium is quite high, 0.67 at room temperature. One can therefore expect time-dependent deformation behavior for lithium. Indeed, using nanoindentation with a Berkovich indenter, we found that the loading rate has an effect. Specifically, at a higher loading rate, in order to push the indenter to the same depth, one has to use greater force. By combining nanoindentation with finite element modeling, we proposed a constitutive relationship for metallic lithium at room temperature. The strength of lithium is indeed both strain and strain rate sensitive. During this study, we also learned that Berkovich indentation is not a very promising way to measure mechanical property of materials such as lithium. As shown here, computer finite element modeling results of loading and unloading curves, assuming different values for Young's modulus and Poisson's ratio. As we can see that the loading and unloading curves are insensitive to the changes in modulus and Poisson's ratio. Therefore, there's not enough information from these curves to uniquely determine the modulus values by Berkovich indentation. However, with flat punch indentation, we were able to obtain the modulus of metallic lithium. And here we use a fairly large size indenter, and then we load, hold, and unload using these equations proposed, well known in the community. We were able to determine the modulus of metallic lithium, and which is about 7.8 gigapascals. The next question, of course, is to study the lithium produced during the electrochemical cycling of the battery, where lithium foil is used as the electrode. As the SEM images show, that the electroplated lithium can have very different microstructure than the lithium foil produced by rolling, for example. Showing here are electroplated lithium using different current densities. Low current density, we see the dendrite size is it's larger than that electroplating from electroplating under high current density. And we also found that the density of dendrites, of course, increases with the increasing current density. And this highly porous lithium is known in the community as mossy lithium. So what would be the mechanical property of such a mossy lithium? Oh yeah, because of porosity differences, the total thickness of the lithium, of course, would also be different as a function of current density, as well as the electrolyte used. So we use this flat punch indenter to load and hold and unload. And this flat punch indenter is sufficiently large to cover a large number of dendrites. So we again measure an average property of this porous or mossy lithium. From this the measurement, we can obtain the modulus of mossy lithium. Unsurprisingly, the modulus of the mossy lithium is lower than that of the dense lithium foil. we can measure the velocity of the indenture during the hold period, and from that we can generate results like this. We can measure for the plot velocity, creep velocity for different types of mossy lithium generated using different current densities in different electrolytes. A surprising observation was found and reported here that dense lithium foil is more easily, it has more tendency to creep than the mossy lithium, as shown here. The creep velocity of this flat punch indenter is much higher than the velocity of the flat punch indenter indenting into the mossy lithium. And that is somewhat surprising, because one would expect with porous material, you not only have bulk diffusion, but you also have surface diffusion, making creep, should make the creep more easier than the bulk lithium. The reason for this is because during electroplating, there is this solid electrolyte interface, an inorganic layer formed on the surface, on the internal surface of the pores. The inorganic material is stiffer and does not deform, does not creep. So therefore, the mossy lithium is more creep resistant than the fresh lithium foil. These measurements allow us to build a model for the conditions at which dense lithium may be formed. And by considering the deposition rate, which is related to the current density, the creep rate, which is related to the porous structure of lithium. And the result is that the porosity is a strong function of the applied pressure, and it's also a function of the electrolyte used. And different electrolyte, under the same pressure, the different electrolyte additives can also influence the porosity of this lithium metal. So to summarize this part of our study, we've shown that at room temperature, the main deformation mechanism for lithium is viscoplasticity. And we proposed a constitutive relationship for metallic lithium. We determined the modulus of lithium foil, and we also show the mossy lithium modulus be lower than that of the metallic lithium foil, but mossy lithium is more creep resistant. These measurements will help us to determine what kind of pressure one needs to apply to the battery cell if we want to use lithium as electrode, as the negative electrode. My final example is about the positive electrode. Since Professor Goodenough's proposal of using lithium cobalt oxide as the positive electrode, there has been a lot of studies in recent years to try to reduce cobalt or replace cobalt by other elements, since cobalt is expensive and it can only be produced in certain locations in the world. So people have developed various ways of substituting cobalt with nickel, with manganese. And as these are layered structures, as lithium goes into the layers, there is still volume expansion, although it's not as significant as in the case of silicon electrode. Nevertheless, people have found that cracking can occur in the inside individual particles of lithium cobalt oxides or lithium nickel cobalt oxides or lithium manganese oxides. And here's an example of it, that after cycling, cracking within the particles were observed. So we wanted to measure how severe the mechanical damage can be by performing indentation on individual particles. In this case, it's a lithium nickel manganese cobalt oxide particle. We can first introduce lithium into the particle by cycling the electrode to a different state of charge, and then take the electrode out, dissolve the electrode, the binders, and harvest the individual particles. Using our flat punch indenter, we can do single particle compression measurements. And this is an example of such a measurement. We have a loading, we first find the individual particle and then load it with our flat punch indenter. At some force, the particle would crumble, and that is defined as our force, critical compression force for fracturing this particle. And we can actually look at the fractured particle, and then most of the fracture is occurring between the grain boundaries, but there's also intergranular fracture that can occur in the particles. Since fracture is statistical in nature, the student performed, again, a very large number of measurements, and then she used the Weibull statistics to extract the average strength of the particles, the fresh particles, particles after first lithiation, particles after first delithiation, as well as the possible influence of the electrolyte. And we learned the electrolyte immersing the particles in the electrolyte did not affect the strength of the particles, but with just one lithiation and delithiation cycle, the strength can change significantly. So we hope this measurement can help us to improve, quantify how strong the particles are, and this information hopefully will help improve the durability and performance of these positive electrode materials. In addition to indentation, we are also doing some scratch tests on the electrode. For example, in this paper, we were able to extract the fracture toughness from a scratch measurement using a formula proposed previously in the civil engineering community when they studied scratch, performed scratch tests on porous materials. To conclude, I hope I have shown that characterization tools commonly used in the engineering, in the surface engineering community are valuable to battery research. Also, there are new challenges and opportunities for in situ characterization of materials for electrochemical energy storage across multiple length scales and time scales to measure the elasticity, plasticity, time-dependent behavior, as well as fracture toughness and adhesion, delamination, adhesive and cohesive strength of electrodes. And with that, I like to acknowledge contribution from a number of graduate students who have graduated and moved on to and continue to make contributions to the development of batteries for electric vehicles and other applications. And I'd like to specifically acknowledge the contribution from Yikai Wang, as you have mentioned in many of these slides, and Yikai Wang and Ding Dan for the work that I presented today. And this is their recent picture. They seem happy with their new baby girl. So with that, I'd like to thank you for your attention and thank you for the opportunity to making this presentation. Thank you.
Thank you for that, Professor Cheng. What we'll do now is we'll hand over to Dr. Ben Beek for micromaterials. We'll give a short presentation. There will be a quick survey to ask if you would like to receive further information from micromaterials, and a few brochures will also be released. So on that note, I'll hand over to Ben.
Thanks, Theckwit. So how do I follow YT's talk? That was brilliant, I have to say. So this is something just very short. And in this short presentation, I'm going to be talking a little bit about multifunctionality in the Nanotest Vantage system, and particularly in looking at how we can gain an improved understanding through combining test techniques, so-called multi-sensing approaches. So normally when I talk about multifunctionality in the Nanotest Vantage system, I'm thinking about the fact that we can do multiple different test techniques at multiple different length scales, because it's 2 different loading heads in the system, and then a range of different test environments, including changing the moisture in the environment and also going up to very high or very low temperatures as well. So normally that's what I think about when I'm thinking about multifunctionality, but in fact we can actually get a lot more out of this system if we think about adding in a multi-sensing capability, so more multi-sensing tests essentially. So the Nanotest Vantage is a horizontal loading, has a very open platform design, and this provides the space to customize and design different types of tests. So some of the things that we've developed over the years are the ability to look at electrical contact resistance, look at electrochemistry, as YT just talked about, and also acoustic emission monitoring while we're looking at either indentation tests, scratch tests, or impact tests, for example. So I won't really say anything about electrical contact resistance because I talked a little bit about that last time, and there's just a paper there how we were using electrical contact resistance as an additional monitoring tool of the degradation in reciprocating nanoscale sliding contacts. So there's a reference there. So as I say, I'll focus this time more on electrochemistry and acoustic emission, just a couple of quick examples with each. So if we think about another situation where electrochemistry could be quite important, this is a SEM image on the left of a so-called retrieved hip prosthesis. This one has failed, and you can see the surface is covered by a large array of different scratches, and it's very sort of complicated to try and untangle that and understand what was going on in terms of that deformation. So what we do with the nanotest is we simplify that geometry to look at single asperity contact, just as I described previously, and that allows us to have a better understanding of the stresses involved causing the different deformation. And we can look at the deformation on the surface and convince ourselves that we see the same type of patterns in the scratch test as we do in the retrieved joints, as well as well, let's just say that we've got a wide range of different tests. We can do single scratches, we can do repetitive scratch tests, we can do so-called reciprocating or nano-fretting tests. We can do all of those things in simulated body fluid and other liquid environments. And I think what's particularly interesting is that we can do simultaneous electrochemical measurements, and that allows us to do studies of tribocorrosion. So this is a very sort of simple schematic showing how the electrochemical, so there's a schematic of the electrochemical cell on the right, and there's a picture of how it looks on the right, which simply looks like a jumble of wires, but I thought I would include that just so you could see what a large amount of space that you have available to design these different types of experiments. So it's a very sort of open geometry, and it's a very simple standard three electrode electrochemical cell, and you have the capability again to use, if you have your own potentiostat already, you can just use that, or we can supply one, whichever is more convenient for you. So an example of where this has been used, in this case at NCATS in the UK, and what they were interested in studying now from a few years ago is looking at, again, this biomedical application. So looking at the, trying to optimize cobalt, chrome, molybdenum hip prosthesis alloys, essentially, which degrade in the body, and there's iron release is one of the factors in the aseptic loosening, which ultimately causes the failure of the joints. So we can reproduce the same current flow with the nano scratch test, and this causes current to flow because it depassivates the surface, so the native oxide is failing. And essentially you can monitor that very accurately within the instrumentation. So you can see a very nice graphic here showing a classic sort of first order decay that's been fitted there. So my other example is again taking advantage of the open geometry of the system, and this is another module that we offer is the integrated acoustic emission monitoring setup, which you can see here on the left. So this allows us to look at the acoustic emission envelope as a function of time in some degradation in any type of test, like an indentation, scratch, impact, whatever. But also we've got this very high frequency, high sensitivity monitoring, and this allows us to look in much more detail at the actual hit spectrum, spectrographs, and in this example here on the right we can see, for example, a couple of pop-ins in the spherical indentation. But perhaps more interesting is it allows us to look at cracking events where we might otherwise not see any information for this. So this is an example of a very simple ramped load scratch test on a silicon carbonitride coating, a couple of microns thick, deposited on a silicon wafer, and this has been scratched with a 10 micron end radius diamond probe, and this is done by our customers of ours in Palacky University in the Czech Republic. And as well as they've increased here, what they found is the first available sign of cracking on the surface is at point B, but we can quite clearly see in the acoustic emission spectrum that much earlier in that process there's some cracking has been detected by the acoustic emission sensor. And indeed the researchers there, they did a focused ion beam cut at that point, and they exactly pick up the subsurface crack that is responsible for the start of this acoustic emission. So it's a very sensitive type of test. So hopefully that's given you some flavor for some of the other things that we mean when we talk about multifunctionality in the system. So the Nanotests Vantage has this very open geometry and this ability to really sort of, it's your imagination that is the limiting factor here. So there's a huge range of these different test techniques that you can do with the instrumentation. I've given a couple of examples where we've looked at it to study nanoscale tribal cohesion processes and also cracking through this integrated acoustic emission sensor. And these multi-sensing approaches are improving our knowledge of complex phenomena and designing better materials. Okay, thank you very much.
Thank you so much for that. So what we'll do is we'll head back with Professor Cheng, and we'll take some questions from the audience if there are any.
Hi.
So hopefully some of the questions should come on screen.
Oh, yeah. I see a question from Professor Yihua Cheng. What is the reason that nanoindentation curves are insensitive towards Young's modulus and Poisson's ratio? And our understanding is that it's so solved. If we use the Berkovich indenture indenting to 5,000 nanometers deep, the elastic rebound is only a few nanometers. And if we have to consider doing that unloading, the contact area may change. So that may be very difficult to actually do very accurate measurement. On the other hand, the flat punch indenter is more suited for this because the contact area is the same. So even though the unloading slope is quite steep, we were able to have a finite slope from which to obtain the modulus of the very soft lithium metal.
Brilliant. So just take
I hope.
Next question.
And
give some introduction about applications of conductive polymers in LIBs.
Okay, conducting polymer. Yeah, certainly it's active research topic using conducting polymer, and if it works, then you don't have to use carbon black. The conducting polymer will accomplish both connecting the structure mechanically and allowing the electrons to go in and out of the electrode. One can develop conducting polymers for that purpose. One can also, as we have done in a few publications, by pyrolyzing, or low temperature pyrolysis of polymers to convert it to somewhat electrically conducting while still maintain mechanical flexibility. So yeah, conducting polymer and using non-conducting polymer, by pyrolyzing non-conducting polymers, one can accomplish the same goal.
Brilliant. Can you explain a bit more about the surface behavior of electrode on basis of SEM imaging?
So SEM tells us about the microstructure. We can learn something about porosity. We can also learn something whether, with EDS, together with EDS, we learn something about whether the surface is coated with what's called solid electrolyte interface, which is a product from decomposition of the organic electrolyte. So usually contains something like lithium fluoride, lithium carbonate, and that can alter the mechanical property as well. So SEM images together with composition analysis, I think are very helpful.
Of course. And the next question is, what about just increasing the pressure within the entire cell, having the casing apply compressive stress as it cools during manufacture?
So perhaps I didn't make it clear that porous microstructure of lithium is the result of electrochemical cycling. So if you use the lithium metal as a negative electrode, and then during the use of the cell, this layer of lithium will be transported back and forth between the negative electrode and positive electrode. And that process is essentially electroplating and stripping. And that's where the mossy lithium is formed. So the initial pressure is certainly important, but also the pressure applied during the cycling of the battery. And as our example shows, that you have to apply quite a large pressure. Whether that's a practical solution or not is still questionable.
Right. And the next question is, how do you do a tensile test on anode material, I believe? And any specific instruments or specific setup is required? Are there any?
We haven't done tensile tests, but these electrode layers are not very thin. They're actually tens of microns or hundreds of microns in thickness. So it's certainly possible to actually remove the metal. So usually electrode is deposited on a metal foil For the positive electrode, it will be aluminum foil. For the negative electrode, it will be copper foil. And we have done, for example, one can corrode or dissolve the aluminum. So you have a freestanding electrode layer. And with a small tensile tester, and you can indeed measure tensile strength. But I'm not too sure whether that is most relevant in the battery application, because during battery manufacturing, of course, the electrode, as it goes through coating, drying, and winding, it certainly will experience tensile stress. But inside the battery cell, I think it's more of the compressive load on the electrode that's important. So certainly, a tensile measurement can be done. I think it can be done, but we have not done it.
Brilliant, thank you for that. Do you find it challenging to locate and position single lithium particles for flat punch indentation? To locate the individual particles, for the positive electrode material, these particles are 10 micron, 10 in size. So that can be found. You can find that under optical microscope. So we found it using the optical microscope that came with the nanoindenter. So it's another important issue is how do we disperse them so you do not have a agglomeration, many particles together. That you can find the proper solvent to disperse them, and then dry it carefully. Yeah. Great.
And that detail is in that paper we published.
Thank you. So next question is, which method did you use for electrode preparation?
That's a very interesting question. The electrode manufacturing, the traditional way, or the most common way, is to make a slurry, because you have inorganic particles, polymeric binder, and carbon black. So people usually have to find a solvent to dissolve the polymer, and then you make a slurry, and then you cast the slurry onto the conductor. And we recently have looked at, so that's the wet process. We recently have looked at, and still exploring, a dry deposition process. There we pre-mix the dry powders together, and then we use electrostatic spray to spray the mixed powders onto the conductor, then going through a thermomechanical process to form the electrode without using any solvent. So I believe several car companies are, at least one car company is pursuing that type of dry process as well. And there they're looking at the extrusion method to extrude the electrode onto a conductor.
Brilliant.
For the work reported today, that was all done by the wet process. And but you can, I'll be happy to send you some papers on the dry powder spray process as well. Yeah, send me an email. Thank you.
Right, so I think our next question is, have you studied humidity/temperature effect on lithium cells capacitance via EIS?
And humidity certainly is a problem, right? So that's why dry rooms are used, because if you have moisture, water molecules can react with the salt in the liquid electrolyte and generate HF, and that can cause a lot of problems inside the battery. EIS is used. Electrochemical, that's impedance spectroscopy, is used, but the interpretation of the data is challenging. Right.
I think the final question is how to measure the electrical conductivity of the coatings, true values without resembling the copper foil conductivity while measuring. That's our final question.
Yeah. Right. Very good question. So we have, for example, after dissolving the substrate, metal conductor, we can perform 4-probe measurement, and but one can also instead of having electrolyte, you can just put your electrode in the coin cell. So you have conductor, your electrode will be sandwiched between 2 conductors, and then you measure the resistance, the DC, the electronic conductivity is perpendicular to the plane of the electrode. That can be done as well. Mm-hmm. But I have seen some papers. People can do some doing 4-probe measurement in very small dimension. Therefore, the electric field, even though you have conductor behind it, the 4-probe is so close. The distance between the 4-probe is closer than the thickness, much closer than the thickness of the electrode, even though you have conductor in the back. And the authors claim that you can actually measure the electrode conductivity that way, because the contribution from the conductor behind it is reduced by having that configuration. Very close 4-probe, closer than the thickness of the electrode. The 4-probe measurement can still work. Mm-hmm.
Brilliant. Thank you so much. I think that's it for our questions. Thank you everyone for your questions, very insightful. I just want to take this opportunity to thank Professor Cheng for this engaging talk. Thank you for sharing such an important area for the future, so we really appreciate your time. I want to thank Micromaterials for supporting this webinar. I just want to remind you all, this webinar will be recorded, and you can find this webinar and previous webinars on our website. So please do visit our website. We will organise the next webinar on the 29th of April at 9 AM GMT time, so UK time, by Professor Carsten on laser surface texturing. So please stay tuned for further information how to register. What we'd like to ask for is your support to take the time to advertise these lectures and these webinars to your contacts. We hope they are as useful to you as they are to ourselves, and we hope you enjoy them as much as we do. So I just want to thank you all for joining us today, and we hope you enjoy the rest of your day, and hopefully we'll see you in a month. So on that note, thank you so much, everyone.